Okay, so we're looking at assignment 2. Now there's quite a few parts of it, and actually passing it turns out to be pretty easy. But there is some work that we do have to do to pass, and there's some work that we do have to do across the program. Yeah, so basically how it works is that we have a few programs. So the first program that we have is PageRank, right? So you have like WN, WI, you've got all this kind of stuff, right? And each of these have different main functions, right? So you're going to have PageRank as a main function. You're also going to have another main function inside of another program for your search engine called Search PageRank. Right? And so I believe there's probably going to be a... Yeah. Okay, so it's quite clever with what it does. It does say 4, but that's wrong. Yeah. So what it does instead is it goes, okay, you've got this PageRank file, then you also have another one called scaled footrank, or foot rule actually. And my typing or writing is better today. And the final one is another main function, which is your search PageRank or something like that, right? These are different main functions, right? So they're going to have argument passing. They're going to, each of them have args, and each of them have, separate program pipelines. Right? But they may share things. So for example, they may share a graph. That's annoying arrow. A graph. They may also share, a list or something like that, right? You get the kind of picture. And so whenever we want to do this assignment, I recommend you basically create a bunch of files and you just start off with the main function. So you always start with the main functions. And what you want to do is you basically just want to create a bunch of .h files and don't implement the functions yet. So you don't want to begin... You don't want to begin writing code, right? Because when you have a pretty big assignment, but more importantly, a very, it's not even necessarily big, it's just a lot of files, right? So when you have so many files, it's really hard to start, and people get really overwhelmed. So if you just start off by saying, I just want to do part 1, and I'm just going to write a .h file for my graph. You could steal one from the labs or whatever, right? Then I want to write another .h file for my, what else do you need in part 1? It's a PageRank. Builds a graph using, I recommend using adjacency matrix. It will make your life easier, I believe. Well, actually, the problem with adjacency matrix is that you need to know the maximum number of URLs. So it means that you'll need to have some kind of function to calculate that. So you have to calculate max before you create. Don't just use some kind of constant. Unless they tell you a constant, but I'm 99% sure they don't. I can't see any constant. If they've got one, then feel free to define it. Whereas if you use a list, then you can just have that dynamic, right? You don't need to calculate. So a list may be better, but it will be more work in the long run, so up to you. And the next thing that you also probably need, yeah, that's mostly fine. Most of this stuff is pretty straightforward. You just have to pass outgoing links, and then you also have words. But right now, for part 1, you don't care about the words. You just care about the outgoing links. I believe you never actually care about parsing the words either. I think you just care about the links for the first part anyway. Yeah, I can't see anything else that would recommend anything else. So really all you care about is creating, I think they even say, oh yeah, they say build a graph structure using adjacency list. So ignore what I just said about using adjacency matrix, because when you have to calculate the max, this is a bit messy. You could still do it, I'm sure. I mean, I wouldn't mark you down if you did decide to do a matrix. It will make some things easier. Honestly, it'll probably make most of the things easier, but a list will be simpler in the shorter term. So probably recommend writing this. But anyway, you write that, then you also write a function for your PageRank, right? So inside PageRank, you probably want a function to define like, hey, you remember you're doing ADTs? So if you want a function for WN, that's probably going to be inside graph.h, or inside the graph, right? Rather than inside PageRank. Or at least part of it will. So you probably at least want like a counter to count the number of outgoing links. I can't always spell. Number of outgoing. And that's probably got to be in the, at least in the graph, right? Anyway, I'm just going to keep going. But yeah, so just create all your .h files, and then basically you just create your main function, and then you call those functions that you defined in here, right? So the point is then you have a skeleton. So you have like, do x, do y, print z. And that's your function, right? And so now since you understand what the code's doing piece by piece, you can go in and you can implement each of these individual pieces, and you understand how it's used. And once you understand how it's used, it makes it a bit easier. Otherwise, you don't really know what you're doing. Okay. And then the next thing that we care about is breaking down this awful looking formula. And what the hell, yeah, not Buenos Aires. No, not the country. The country of the formula, yeah. I mean this, no. I mean, I did try to do it, but I don't think it let me. I'm gonna redo it. Okay. I'm trying something new. I'm trying to be able to I can like copy. I feel like I'm being a winner if I'm doing stuff like this. I should be able to, yeah, this is what I want. Yeah, copy this. Yeah, there we go. Awesome. Okay. So we have this pretty cool looking formula here. And we have a few parts of it. And the other part of it is we have this equation here. Where we've got pi semicolon 0 equals 1 on n. Right? And so this seems a bit weird. I'm sure, well, hopefully it doesn't seem too weird, but it does seem a little weird. Because people often look at this and goes, what the hell does this mean? Like, what's t? Like, okay, we use t here, but what? Like, this doesn't make sense. It's just weird, right? And the reason why is because basically t is your iteration. So what you're basically saying is I have to run this algorithm a series of times, and I get something what's called a recurrence relationship. Right? And a recurrence relation is basically something like Fibonacci, where you say Fibonacci of n is equal to two conditions. It's equal to 0, equal to 1 when n is less than or equal to 1, or it's equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2, given n is greater than 1. So when we have something like this is a recurrence. Basically means it's recursive. Right? However, in our case, instead of going down, see how this goes down? This goes up. It builds upon the previous one. I mean, technically they're both going down, but what you're going to be doing is you're going to be running this, and then running this again, and then running this again. So for something like this, you want to use a while loop, right? And not recursion. And if you actually look at the assignment, there'll be there's a section for pseudocode, and you'll see it says while iterations less than max iteration and so on, and that bit of pseudocode is effectively your t, right? Now you don't actually care what the value of t is at any point. All you care about is what was it previously, and that's it. So that should hopefully give you enough of a hint of, kind of how you're going to be using it. So the next thing we want to look at is in and out. And I want to be careful of time because I don't want to waste too much time. Okay, so in and out. And what's the equations for these? I believe they give you a really complicated equation, and then they also give you a really simple equation. Yeah, so the really simple equation is still not that simple. So they define it like this. I think that's called I. No, they do call I. So they go W in given two parameters. It's not really a parameter, but it's kind of like a parameter. Is equal to O, whatever O is, divided by this crazy weird looking E, P inside R of V, right? Of OP. I'm just going to copy and paste it. I immediately decided that was a bad decision. Okay, because writing math is hard. Okay, copy, paste. Yeah, it actually worked this time. And you can have my cursor forever, because apparently my cursor is never going away. Can I trim it? No, I can't. Oh well, it'll cope. So this is our equation, right? So we have our W out, in this case it's W out, but W in basically looks the same thing. The only difference is, I think instead of using O, they use L. I can't see it on this link, but I'm sure one of the links it will say it. Yeah, so they use I guess for in. That makes sense. But you see that the equation effectively looks the exact same, right? And that is intentional. So these two equations look very complicated and annoying and hard, right? Because O is weird and P is weird and all this kind of stuff, right? So I like to actually rephrase how they're written because I think it makes more sense this way. So instead, I like to say that the number of outgoing, right, for any node V and U, right, I'm basically just going to give these contexts more words, effectively, is the number of number of outgoing, right, of U. So this is the number of URLs that go out of U, divided by, or num outgoing of P, where P does not equal U or V, and P is adjacent to V. Right? That's like a rough estimate of what it basically is. Right? So it's all the reference pages. Okay. That's good. In links is 2. Yeah, it's easy, awesome. Okay. So it uses this really confusing terminology called a reference page. A reference page is basically any adjacent URL. That's it. If two nodes are adjacent, they're a reference. They can be adjacent in any way. They can be outgoing, they can be ingoing, they can be both. Okay. I believe this is correct. Yeah, it looks correct. Okay, awesome. So the number of inlinks of this is that. Yeah, you just care about those. You want to make sure it's not the actual node itself, which is awesome. The actual mistake I made here, though, is that it shouldn't be you here. Yeah. I was looking going, that feels wrong, so it looks back at the equation. Yeah. So you just care that it is adjacent to V, it can be the node itself. So I'll do an example. So what I'll have here is I'll do this example based off the thing they gave you. I'll just make it slightly different. So we have A, we have B. These are going to share a page. They're also both going to have an individual page. And their individual page will be unidirectional, i.e. both ways. Yeah, bidirectional, doesn't even matter. And then these will just be in links. And then this page will also link to some other page. Right? And so we're going to call this page 1. We're going to call this one, mice decides to connect. There you go. Page 2, page 3, and page 4. Awesome. Okay, let's keep going. So now we have all these pages. Let's calculate what these values are. Right? So if we want to calculate in, we have to care about what ones. So we're going to calculate in. Now V is basically, you can think of V as saying here is kind of our main reference. It's like basically almost like an entry point, I guess. And then you want to calculate the other coordinate U. Now you'll be doing this if you actually look at the equation itself. Yeah, ignore that. Here it is. You look at it, you'll be calculating W in and W out for all values adjacent to your PI. So for each URL, you'll be finding all the values, right? So you're summing up all the ins and all the outs, effectively, right? You're creating like a matrix. And that's actually what I recommend you do. I recommend that you create a matrix, which is just a fancy word for, in this case, a two-dimensional array of n. I guess instead of n, I'm going to call it, what do they call it? Let's see, they call it, they do call it n. Okay, so it's going to be an n by n matrix, right? Or 2D array, i.e. you'll have something that is a double pointer, right? And it'll be an array it'll be a pointer to an array, where each of these elements will also be an array, right? And so on. Awesome. And then what will happen here is this A, if we want to calculate the A, we have to give it an individual value. So in this case, we're going to calculate P1. Right? So what we want to do is we want to calculate the ingoing, obviously you swap this for in because we're doing in rather than out, the number of ingoing into this node, right? And divide that by the number of ingoing for all nodes related to A. So you'll notice something here. This is kind of like TF, and this is kind of like IDF, right? So you'll notice that almost all web algorithms, when you're doing searching, all have this kind of behavior where you have one general statement about a website, and then you have one very specific statement about each page. There's actually a term for it, which I remember saying it before, but I don't remember what it is right now. It's something scale, right? And the whole idea is that basically you have some scaling factor that kind of bias. That's actually the word I was thinking of. It's called a bias, right? So you're biasing your values by some kind of almost like global kind of value to that corpus of pages. So in this case, the number of ingoing of P1 is just going to be 1. There's just one value that goes into P1. So it's just going to be 1, right? Nothing too fancy. And then the number of outgoing, the number of outgoing of P1, so the number of outgoing of P1 will also be 1, I guess. I'll do that as well. Right? So this will also equal 1. Now, this bottom value is going to be calculated for all values of A, so we can do it together. So for A here, or as I like to say, all outgoing or all ingoing, right? So that's going to be for this, and then there's also going to be one for ingoing as well, right? So the in value, which is going to be here, is basically just find all these nodes here and calculate this and just sum it up. That's it. It sounds a lot crazier than it actually is. So in this case, it's just going to be 1 plus the same value for this. Now, how many ingoing nodes into P2? There's 2. I can see 2 right now. So it's going to be 1 plus 2. So the total value of this is a third. Awesome. We're going to do the same thing for out. How many outgoing nodes for P2? 1. How many outgoing nodes for P1? 1. So what do you think the total value is? A half. Awesome. Now they do tell you something. They say, hey, if this ever equals 0, don't make it equal 0, make it equal a half. Right? Or 0.5. So make sure you do that, but that's fine. I don't really care that much about that. Okay, and that's it. That's basically all you're going to do it, right? And you're just going to be doing that for every single value overall. And then just basically be summing up all those values, and that's going to be it. And so honestly, I think that's probably good enough to begin with that part, right? I think just honestly, as I said before, write out some header files, try to work through it. Hopefully that gave you a good enough understanding of what we're really doing. But if you want a bit more understanding about why this works or whatever, then I'll give a quick explanation. Okay, so we're just going to create a pretty simple network here. And this is just going to go out, and then we're going to create some edges. Okay, so this is our node here. Now this is a series of pages. Now we may want to do some searches in these pages. We may want to search for cats, or pugs, or I don't know, axolotls, however you spell them. So regardless of what we want to do, we want to know some information about these web pages. And so there's 2 ways that we can do information currently. So the first way that we know is we know that we can do TF-IDF. This is one way that we've already seen. The other way that we'll learn now is something called PageRank. Now there's many, many, many more ways. I bet you Google probably has probably at least dozens, maybe a bit less, I don't know. They've got tons of different methods, and then they combine them all together at the very end to choose the best selection, right? And now there's multiple ways that you can do this best selection, right? But this best selection is something called an optimization problem. So if you want to get, if you're really interested in it, then there's extra marks. I guess it doesn't really matter much because it's a pass or fail, but still. And the extra marks are if you actually do a better algorithm. Now the one I came up with was n cubed, which is obviously quite a bit better than n to the factorial. That's when I did this assignment ages ago. And it uses something based on the Hungarian algorithm, which is a bit of a weird name for an algorithm. It's a very hard algorithm to implement, so I probably don't recommend doing this if you're faint for heart. It'll be a very long time to implement it, because it's effectively quite simple conceptually. It's basically just a matrix reduce operation, if you know what that is. Using something like a Gaussian reduction or whatever. But the problem with that is that it's quite hard to do that in like on a computer. It's easy to do it by hand, but computers need to do all these things called like what we call starring, which is basically where you said, hey, I can reduce this column, count the number of zeros in columns, and it leads to, I think, at least a couple hundred lines of solutions, easily, potentially much more. Okay. I'll run this mouse decides, nope, I don't want to. Yeah, okay, it's back. So, yeah, so whatever, you can do it if you want, but probably recommend you try it. There's simpler algorithms out there that are less efficient. This is probably the most efficient I've heard of. I bet you probably could. There is a maximum limit, and the maximum limit is going to be n squared. I believe, because if you have n methods, and you have n items, then obviously you go try every method for every item, I guess. So it's probably going to be n squared as a theoretical limit, but you may find that we can't reach that because of other conditions. Kind of like how the theoretical limit for searching would be like 01, you just like guess and you get the right answer. But obviously we can never hit that theoretical answer, right? Or 10, that's not correct. But anyway, who cares? Continue. So the other method is something called PageRank. So PageRank is interesting because it's almost like a competition. So TF-IDF was very individual, right? It was like, I care about the content on your page. PageRank doesn't really care about the content anymore, right? TF-IDF is much more based around, well, how much do other people care about you? So, so PageRank, I think I said TF-IDF, is that PageRank is like others' opinions, right? Which you probably shouldn't listen to normally, but here it's good, right? So we want to listen to the opinions of the other pages, what they think of us, And so in this case, we instantly can tell a bit of information just intuitively. The first bit of information that we can tell is that if we're on A, we go to B and we go to D, but we never go back. So you can think of it as like A, is best friends with B, but they're not best friends back, right? But there's no reciprocation. And we could call that as an intuitive understanding of what's happening here. And so effectively, this becomes a rating that we can use. And so intuitively, there's a bunch of information that we can know about this. And so this is really what I care about here, is whether or not it's reciprocated or not, is really kind of what, honestly, the basis of PageRank is that if all these pages, as you can see how almost every page goes to B, especially if I have this connection here, and this connection here, if all these pages go to B, then that means B is thought of very highly. So if I'm on any page but B, right, and I want to go to B, go for it, right? So it's basically the kind of thing of like if B has like cats on it, then B's perfect for cats, because all these pages rely on it. So it's got a high ranking. But if I'm thinking about going out from B, and I want to go out from B and find something else, then B isn't necessarily my best choice because nothing ever comes out of B. Or except for maybe, let's say, C or something, right? And so it's almost like it only cares about the direct links. But it does also kind of care about this other thing, as we saw previously on the previous page, I clicked the wrong button, where we care about all the number outgoing. That's kind of like almost like, it definitely isn't recursive, so don't think of this function as recursive, but it is kind of like one level of recursion. So it's almost like we're going out and we're going, okay, find me all the things connected to you, right? Including this. So, but definitely don't do it recursively. It probably should just be like a while loop that says, hey, go through, it's the same while, let's say for. So for all P such that, P adjacent to some magical value V, right? And this is my, value that I'm looking for. This is, if we look back here, this is this, right? Oops. And we want to find all of these, and you go, okay, sum up, outgoing, or ingoing, or whatever, right? That is awful spelling. But anyway, so that's effectively it. You got your algorithm down pat. Now I'm gonna stop it here to prevent this going forever. But hopefully that's a good start. Let me know if you can obviously email me or anything. That should help us out the Ciao.